Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode, I'm joined by Ashutosh Saxena, a veteran of Andrew Ng's Stanford Machine Learning Group and co-founder and CEO of Caspar.ai. Ashutosh and I discuss his RoboBrain project, a computational system that creates semantically meaningful and actionable representations of the objects, actions, and observations that a robot experiences in its environment, and allows these to be shared and queried by other robots to learn new actions. We also discuss his startup Caspar, which applies these principles to the challenge of creating smart homes. Enjoy. All right, everyone, I am on the line with Ashutosh Saxena. Ashutosh is co-founder and CEO of Caspar. Ashutosh, welcome to This Week in Machine Learning and AI.
Yeah, sounds good. Looking forward to the chat today.
Absolutely. Let's get started by having you tell us a little bit about your background and how you got to get working in ML and AI.
So I joined Stanford University back in 2005 and met Andrew Ng. Andrew Ng was a professor in machine learning and doing some interesting stuff with flying helicopters upside down using machine learning. So that's how I got started into the area of AI and machine learning, did my PhD there. Since then, I've been applying it to robotics, computer vision, natural language processing, and more recently into the smart home areas. It turns out AI is a very powerful tool, so it increases the impact and the things that you can do with it.
Talk a little bit maybe about how, where you see the implications of AI in smart homes. It's not a connection that we hear about too frequently.
So it turns out AI is very powerful when the situations and what you are trying to do become too complex to program manually. So earlier, before joining Caspar, I was a professor at Cornell University for a couple of years trying to program robots to do things. And it turns out when you have robots in people's environments, it turns out the home environments are very complex. Everyone's home is different. People do activities differently. There's a lot of variation in the way people speak. And the way people do things, and just the visual information that you get from the cameras. So for a robot, you're trying to understand what people are doing, how people are speaking, what a robot can do for them. Now, similarly, in the smart home space, if you think about some of the devices, such as the Nest thermostat built by Google, or Amazon Alexa or Google Home, built by Amazon and Google for conversational purposes. They have a really challenging problem because you are trying to control the environment in people's house, such as climate. And then what you are dealing with is people who have a lot of variability. So you have a speaking conversational system, which is trying to speak with the person, and every person would speak differently. Similarly, in Caspar homes, we control lighting, shades, cameras, microphone for conversations, sensing for elderly and seniors. So there are a lot of things that we do in the homes. Such a big variation in the data that it becomes very hard to manually program these rules. So just to give a very simple example, let us say you talk to a home and say, I am watching TV, too much sun. So close the curtains. This is what your intent is. Now, people will say it in a variety of ways. So you cannot write a computer program saying, if person said these words, then do this. If person said something else, then do this. And the situation is also has a lot of variability. If you're watching TV and there is too much sun, it probably means that the sun is shining on that particular day, so you cannot see the TV. And the right action is to roll up the shades or close the curtains and turn on some lights in the background and stop the music which was playing. So all of this home applications with Alexa, with robots, with Google Home, and with Caspar, it requires a lot of data processing and understanding of the context to be able to do things. This is where the AI becomes extremely powerful because it's data driven and one can create actionable items to improve and do things for the people living in the homes.
You've talked about the challenges presented by smart home environments in terms of the variability of the different types of data and the way questions are answered and all the different contextual information that a system needs to keep track of to do what a user wants. One of the projects that you've been working on to address all this is something called RoboBrain. What is that?
Yeah, so it turns out that in some of the areas, a variety of data and collaboration through data helps a lot. So in the area of computer vision, a lot of researchers have been collecting images and putting image labels, like if there is a car in the image, if there is a person in the image. And with this data, it really helps the computer vision algorithms to train and develop better techniques and use things such as deep learning to build these classifiers. Now it turns out in the area of robotics and homes, such progress hasn't been made that well. There have been some attempts, but lack of data means that every researcher, every university was redoing the same things over and over again. So that's why we started this RoboBrain project as a collaboration between Cornell University, where I was, Stanford University, where I did my PhD, and a couple of other places such as Brown, and so on and so forth. And what we did is we had robots at all these places. And the idea was when robot is performing and learning in these individual environments. For example, a robot at Cornell may be trying to listen to verbal commands and trying to make a simple kitchen recipe like affogato or trying to operate a coffee machine. A robot at Brown University could be trying to learn how to pick up things and put them back. And a robot at Stanford University may be focusing on image classification tasks and how to figure out how to see things. And the idea is if we can pool all this information together in a good learning representation way, then suddenly this project enables all the robots, and not only just the robots at these three universities, but at many other places more powerful. Historically, I think 10 years back when I was doing my PhD at Stanford, our group was developing a lot of these robots. And one thing that came out of this effort in Andrew Ng's group was called Robot Operating System. So that was an effort of a similar kind where the robot software was open sourced through Stanford, Willow Garage, and many other universities. And it allowed a lot of different groups to collaborate sharing their software.
I didn't realize that ROS came out of Andrew Ng's lab.
Well, it was a collaboration that started out from Morgan Quigley, who was doing PhD with Andrew Ng. And then Willow Garage really helped to expand it with a variety of new people joining at Willow Garage.
Okay, cool.
And ROS at that time was a very small project where we were just trying to make sure that a couple of universities could actually connect our software to each other. And now, like 10 years later or 8 years later, I saw a very similar situation where people were developing machine learning algorithms individually in different places. And a centralized effort did not exist to bring all these learning skills for robots together in one place. And that's why we started this RoboBrain project.
So if I can maybe paraphrase that, what I think I heard is that you're trying to train robots on a variety of different tasks, and you want a robot learning thing B to have some benefit, to be able to learn from what another robot learning task A, learned. One way to do that might be to kind of share the model that it learned. Like if you're training a deep learning model, you share that from robot A to robot B and vice versa. But it sounds like you're proposing something a little different than that. Is that right?
Right. So some part of it is one way to share things is you share a learned model from one robot to another. So a part of RoboBrain is to allow to do that. But a part of that is also to become a platform such that it becomes a good representation to figure out what model to share. To go deeper into one example, let us say you are trying to make a kitchen recipe like affogato, which is take the ice cream out, put some coffee in it. Now, for this, you require machine learning or deep learned models for computer vision, where you are doing classifications. You need machine learning models for grasping, where you are telling how and where to touch the objects in order to pick it up. And then for pouring that recipe, and also models that allow you to parse language into actionable items. So you need a variety of these models. So you first need a representation that allows you to compose these different deep learning models together, which is what RoboBrain does.
And is it fair to think of it as metadata for describing different situations, or is it representations more in the mathematical sense, where there's maybe some vectorized or semantic representation?
So I think one way to think of that is, let's take a simpler example like a dictionary. What a dictionary does, or a thesaurus does, is, or even Wikipedia, for example, is that it has topics or like words, and it tries to explain the meaning of existing words in relations to other words through some qualifiers. So there could be a word called running, and the way you would explain running is it's walking but with a faster speed. So now running is explainable with two other terms, walking and faster and speed, right? Similarly, now let us take the example of RoboBrain. So you're right. It is essentially one can think of that as a graph. In the graph, there are not just words, but also physical situations such as how to move your arm or robot's arm. How does visually some neurons look like? What is the spatial relation between two objects? And these items become nodes in the graph. And then the relations between these edges is an explanation of that concept. So to give an example, if someone says, oh, I want to pick up a cup. So the semantic node of the cup would be connected to the table, because cup is usually on a table on a countertop. But it would also explain in this case that cup is usually on top of table, and it would include information about XY coordinates, Z coordinates. That cup is usually 2 inches away, or the bottom of the cup is touching the table. And that helps the robot quite a lot, because if it can find the table in the environment, then it becomes much easier to find the cup. And then the cup will also be connected to the handle, with the information that the handle is usually used to pick up the cup, especially when there is a fluid inside the cup. So there would be a heat map of sorts on this cup that looks like a neuron, which if you run that machine learning model, it would find that handle. So it becomes like a Wikipedia for robots, where you're not just linking words, you're actually linking semantic labels with physical locations through these different models.
Interesting. I often hear when we talk about one of the challenges of deep learning or AI more generally, this idea that we can train a model to do things, but there's this whole broader concept of common sense that helps us as humans navigate within a world and do different things. It sounds like part of what you're trying to do with RoboBrain is find a way to encode all of this common sense. For example, that cups usually sit on top of surfaces, that when they have liquid in them, that liquid can spill, that you want to hold the handle in a certain angle so as to not do that. And then that becomes this RoboBrain that can be shared between robots doing different tasks. It's almost like the Google Knowledge Graph for textual data, but with between not just textual data, but also actions and kind of these semantic relationships.
Exactly. So this is what it is. That's why sometimes we call it Wikipedia for robots or knowledge graph for robots, because in addition to symbols and hyperlinked documents, it basically contains 3D information about the real world and appearance models and so on and so forth, or actions that are relevant for robots, like how to pick up and move the arms. And it's a graph, but the variables here are semantic, spatial, and things that are relevant for the real world.
And so when I think of the full power of something like this, and even the example or the analogy to Wikipedia, this thing is most powerful when there's a single instance of it with lots of people contributing to it? How well defined are the interfaces to this thing such that, lots of people can contribute to it? And is that happening yet?
So it's a university project, just like robot operating system with Morgan Quigley and Andrewing was a university project in the very beginning to prove a point. So at this stage, it is still a collaboration with just 2-3 groups, a university level project, RoboBrain, where we showed that a robot being trained at Cornell with the RoboBrain hosted at Stanford could be used to have a robot at Brown University in a different part of the country pick up objects and do something. So we actually showed that loop being completed through these interfaces. The interface here is the graph. So you can query the graph, get all the information from different models, and make it happen. So it's not in an industry ready state, but I think academically it proves a point.
So maybe walk us through, before you move on, walk us through that specific proof point. It strikes me that you can, without the details, that can either be really interesting or not all that interesting at all. Like as is often the case, the devil's in the details. What specifically is happening in this scenario, and what's the graph that's being transferred? How is it transferred? Or all those are kind of the questions swirling around. What's the best place to start with that?
Yeah, so maybe that's a good idea to dig deeper into this particular example. That we did a couple of things, but we can take up one example on how the graph would look like and go a bit deeper here. So let us see. So let's take a very simple example of it's not simple from a robotics point of view. It's something which is very simple. Just pick up the cup is actually very hard for a robot to execute, but things are getting better. So the scenario is that there is a robot, 2 robots actually at Cornell University, and one of them is trying to match the object parts to actionable items. So this project was done by my PhD student called Jae Sung, and the project name is RoboBarista. It essentially goes around in different buildings on campus and uses something which is known in computer vision community as a part-based model, like object part-based model, but more focused towards robotics control and manipulation. So just to give some examples, it goes around to a light switch and in 20 buildings and it operates them. Now it has a model that if the light switch looks like this, then it can touch it from the top or the bottom in this particular way and turn on the light, right? It learns how to operate the switch. Then it goes around and finds all the buttons on the campus and it tries to keep pressing them. And then it correlates how the button looks in 3D and visually and tactile and how do you press them. And then it goes around and touches all the handles or levers and tries to operate them. Now it comes back and it does some machine learning and it produces some data in models. And the data looks like the following. This kind of input data, which it represents using a deep learning model, correlates to this action. For the symbol buttons, for the symbol switch, this is how it looks like. So these become some nodes in the graph. The information is not complete yet because it's not usable at this point in time. Now, another PhD student was focusing on a project called Tell Me Dave, called Dipendra Mishra at Cornell. And he's focusing on how to now use this 3D and joint angle information and link them semantically. So his focus was on natural language processing and mapping them to symbolic actions. So his project is, how do I make affogato? So affogato, you go to a coffee container, try to use a lever to pour coffee in the cup, and then you take a cup and it has some ice cream in it, then you try to put some raspberry syrup in it and coffee in it. Now let's think about it. It is actually reusing similar actions from the other project, which is how to operate the lever, how to hold a container and move it around. So in this case, the graph gets appended with additional nodes and additional edges. So the nodes here become cup, lever, and that if you press the lever, then something comes out. And there is an online recipe. So now you're basically extending the graph here, right? So this is what the graph that was created at Cornell. And then we went to Stanford. There was a group with Silvio Severis, professor in computer vision group, and they focus on computer vision appearance and part-based models and so on. So there, with a couple of other people like in the group, PhD students like Ozan Sender and Ashish Jain, we built this 3D model, which is a cup is on the top of a table. So let's collect a lot of data about cups on the top of the table. And from the data, you would learn that a cup, when it is found, is at a certain pixels or certain inches away from the table. And you would try to pick up this cup many times. So now this graph has a lot of information. It has information about that the cup is on the top of a table, how to use levers and buttons and so on. Information may not be perfect. That's okay. Now what happens at Brown University, that we have a different robot called Baxter in Stephanie Telex's group. And what they are trying to do is really make grasping work very well. But it turns out that the grasping, the way you grasp as in like pick up an object, actually differs from object to object. Like a whiteboard eraser or a pen lying on a table, you would pick it up from the top. And a cup, you would try to pick it up from the side because you don't want to affect the liquid in the cup. So they are focusing on this robotic action of picking and closing the gripper. Now what we showed is that if you query the graph with whether it's a cup or a whiteboard marker or a certain type of object, then you would receive the information that these are more probabilistically likely areas for doing the grasping. So that Baxter robot queried the graph through an API, and then we showed that with and without that information, the grasping performs better.
Within that explanation, there are so many little details that individually are difficult problems in computer vision and robotics. Navigating around the campus is, there's still lots of interesting problems around there. Even identifying what might be a switch so you can start to poke at it and determine, what might be the actionable surfaces, and then to kind of abstract away from that to identify that the switch has a top and a bottom. Like there's so many individual challenging problems in robotics and AI. Rewinding that description a little bit, what are some of the simplifying assumptions that were made in these different kind of sub-problems?
I think we realized that. So within a couple of these groups that we were working with, that was actually the biggest discussion point, because each of these problems like navigation, manipulation, computer vision, language understanding, and so on and so forth, we involved, I think, like 5 different research groups. Natural language research group at Stanford, machine learning group here, computer vision group there, and so on and so forth. The biggest discussion point was what is the representation? That became the biggest question, because and that actually also highlighted the difference in the different specific fields. People get a little bit too narrow. Like language, people think about things in symbolically, like a cup and tea and mug and drink, and they forget that drink and cup has a physical meaning. It's actually a 3D thing. And the people in navigation only think about 2D. I took the robot from here to there, but it's not my job to, and the robot was not close enough to the door. And it turns out that if it's not in the right position, you cannot operate the arm to open the door. It's just kinematically impossible. And so on and so forth. So this was a good exercise in a way to come up with these representations. So some good outcomes came out of it. So one good outcome was the relation between the natural language symbols and 3D and spatial information. So when you start having things like pick up or grasp or on top of, like a cup is on top of table, correlated with the actual 3D or spatial world, it becomes very powerful, because now you can say cup is on top of table. Well, next time a mobile phone could be on top of a table, but you don't need to observe it with 10,000 images. You can reuse the semantic notion of on top of to now extend the 3D information that you just learned, that cup is on top of a table, which means that the bottom part of the cup is on touching the top part of the table. It's very powerful 3D information, right? it goes to the mobile phone now and laptop and so on and so forth. And suddenly this transmission of information happens, and you can start extending the knowledge. I'm not saying this is complete, but that's the idea that we were going towards. So other than this extension and correlation of different pieces, the one other good thing came out of it is in the area of deep learning. It was a CVPR paper that we wrote in 2014 at Computer Vision and Pattern Recognition. It was best student paper over there. And what we found in deep learning area is that most of the models are put a vector in and get something out. They are not interpretable. I mean, there are exceptions, but majority of the work in deep learning is not interpretable. You cannot put common sense or existing knowledge into these models. And that was a little bit orthogonal to what many people were trying to do in robotics, where there is information which you want to reuse. So what we developed was called structural neural networks, which essentially what they do is, instead of trying to learn a big giant model which can only take one type of data and produce one type of output, you start producing these recomposable models. So each module would focus on one specific thing, and they would dynamically connect to each other depending on slightly different situation. And that allows it to extend really, really well to different data sets with different input modalities and different situations.
Your description of the effort around identifying the representation reminds me of, I don't know if you've come across the term master data management from kind of the enterprise computing side of things. But it's basically like a large company will have, these different divisions, and, they all have customers, but they all think of the customer slightly differently. So they go through this MDM effort to really net out, like, what is a customer? What attributes does a customer have? Independent of where they represent a customer, whether it's a CRM system or a ERP system, whatever. And they do this for kind of all of the entities that they have to track in all of these different systems. And it sounds like, part of what you're doing here is like creating a master data management system for, the objects that these robots will have to manipulate.
Yeah, actually, I did not know about this MDM, but looks like, we are doing something like that. Except that instead of, when we think of data, we actually mean learnable representation. So I would call it master representation management for robots or something. So that would be a little bit more apt analogy.
Yeah. And so you were careful to say learnable representations. What are the specific implications of that learnable element?
So this learnable part is actually quite important. So what happens in a usual like a dictionary sort of graph? I mean, you can represent a dictionary as a graph, right? It links words to words through some explanations and synonyms and so on. That it becomes fixed, and the links do not adapt because the variability in a language dictionary is finite. But when you are working with more complex models, such as Google Knowledge Graph or other elements, the variability is very large, and it has to adapt much faster. So just a simple example, like, let us say you observe that a switch can be flipped up to down, but a switch can come in three different forms: a up down switch, a press button switch, or this toggle switch. And robot may not have observed all the three switches on the first data set collection. So therefore, you need to have a representation that, given more data, it can add to this information. Like, it learned a model about the switch and the finger, that, whenever a robot finger goes to the switch, you can turn it on, and it learned something. But it cannot be fixed. Like, next time more data comes in from another place, maybe we connect to Japan and they have slightly different switches there, which they do. Then it should be adaptable. So that is how I think this representation would improve over time and become, with every action or every learning that happens anywhere for robots, this representation will keep getting better for everyone.
And I'm curious, practically speaking, how is this this representation system that is ultimately queried, how has it been implemented? Is it like graph databases or, a simple relational database or, something else?
Oh yeah, I think it's basically implemented as a graph, and it's a simple. It's actually a sparse graph, right? Because not everything is connected to everything else. So it is stored as a sparse graph. And one thing we have is what that we call as robot query language or robot query library. And this graph provides a certain type of interface. So you can query the graph saying that, oh, give me everything that is connected to this node, or give me everything related to the tactile links related to this. So I want to operate a cup, but I only care about tactile information. So it allows certain type of queries. It also has other complex queries like give me the most probable answers, because sometimes it has each query may result in a sequence of answers like, oh, for grasping a cup there are these 5 locations usually, but some robots may want to query all 5 so that they can optimize according to the situation. On the other hand, some other situation may just want the top one, max probability query. So that's how it is implemented.
And do you use this RoboBrain system at Casper, or have you built a separate set of systems at Casper?
So I think what happened about 2 years back, this is more of my personal story as compared to RoboBrain or Casper's story, is I was looking to see how can I take these ideas and this opportunity to a bigger impact. And I realized that in order to make people's lives better, if one starts thinking about people's homes, it's a really big impact situation, because a lot of people have homes and not many people have robots. So I started talking to real estate developers for elderly housing and for normal housing as well. And I wanted to create a similar sensing scenario. So it turns out at Casper, it's a robot inside out. So it's a robot in which people live inside. So our home has same level of sensing, in fact, more than a typical robot. It has cameras, microphone, motion sensors, thermal sensors, so you can see where people are and what they are doing. And the local AI respects privacy, and then it starts to learn in a similar way that if some elderly person fell down on the bathroom floor, what to do about it, and so on and so forth. So it turns out that the techniques and ideas are similar, that you have to learn from homes and share this information and so on. But in technical detail, we are doing different things as compared to RoboBrain.
Okay. In the Casper scenario, you mentioned, for example, learning that that someone's fallen and what needs to happen. How would a robot or a robotic home do that without some specific training and guidance?
So the ideas are similar to what we talked about. The details, algorithm, and techniques are quite different. But let me give an example about the falling. So it turns out that one can start thinking of that as a recomposable deep learning representation. So there may be a model that can detect objects. There may be a model online that can detect human poses and track people. There may be a model that knows about geometry. Now, in a home situation, you take these recomposable models, put them to detect falling. So this is how you are reusing information. And in some of the houses, what happens is after people fall, they ask for help, and the expectation is that, oh, someone may be available to come there and help. So Casper knows that whenever a person fell down in these couple of houses, it was an important scenario that someone may have been called. So it starts to adapt. And now we are building a whole 132 senior home complex near Vegas. And now it has learned a lot of such things, that if people don't get up on time in the morning, then there is something wrong about it. Like sometimes seniors don't get up in the morning. People have a certain pattern for drinking water, and it turns out that many elderly people forget to drink water. And that's how it keeps on adapting from these situations by looking at data from different sources and tries to address those problems.
I'm trying to come to terms with a very high degree of skepticism. And, it's really, I think, around this idea of undirected robotic learning, meaning, how does the thing know what its objective function is, for example? What is it trying to optimize without some operator telling it that, these are the things that it's trying to optimize? Does that make sense as a kind of a half question?
Right. So let us take a example which is a little bit more concrete toy example. It may not be as impactful as senior falling for discussion purposes. So we can discuss some of these important points like objective function and action variables and so on. And this example could be, let us say Casper Robotic Home is trying to learn trying to adapt the wake up function in the home. So usually in an alarm clock, you just beep the alarm clock and people either wake up or not. But in Casper Home, Casper can make a sound to wake you up, play music, open curtains or shades for natural lighting in different rooms. It can turn on the lights. It can even flash the lights and so on.
And even before you go further down this example, there is an assumption that, someone, a developer of Casper, decided that Casper should be trying to worry about when people wake up, right? It's not like it just saw that, hey, people tend to wake up. And so it's, maybe I should optimize this, right? This is a feature of the system that you've built.
Right. No, you are right. So I think there is a little bit of human guidance involved here. It's not a free AGI. So certainly, I think the level of representation that we manually guide the system is that there are these things called activities that people do. And there are these things called these devices that you can operate in a certain way. And you can do crazy things with it. Like don't close the curtain 5 times in 10 seconds otherwise. So there are certain limits and constraint that is given to the system.
Okay.
So in this particular case, what happens? There are, let us say, 5 variables: music, sound, curtains, fast, curtain, slow, and lights, bright, lights, dim, and so on and so forth. So these are the actions. The input variables are how many people in the house, when was the person sleeping last time? Did he explicitly set an alarm or not? Is it weekend versus weekday, summer, winter, so on and so forth. And now what happens is you have input variables and output actions, which have to be mapped to each other. And let us, for the time being, assume that they are perfect and they exist. The part which becomes interesting is how do we take feedback and the objective function? So here in this case, what happens is the feedback is sort of an imitation learning because Casper doesn't do it the first day. It kind of observes. So it sees when people open the curtain. So it turns out, surprisingly, that there is kind of a clustering of behavior of 2 types of people. One set of people like natural lighting and wake up very fast within a few minutes and they are active, like they jump up from the bed and move around. And the second type of people are kind of just stay in the dark, sluggish until they get their morning coffee and they like it bright. There's a spectrum of people, but we have found that there are these clusters. So Casper starts to learn that this person is like this because he took the action of opening curtains manually. So a couple of times he may have opened the curtains manually. Casper opened curtains. Casper turned on the lights. And he may have done it more on the weekdays when he wanted to go to work versus weekends. So those become the signals or supervisory signals. And that starts to get enough data to map the input to the output, which is activity wake up, and the situation of number of people in the house, morning time, weekend versus weekday, to what to do, curtains, music, bulbs, and so on.
Okay. So what I heard, I might explain as, part of what you're trying to do is build, like if you think of the Nest thermostat, right? It's got, a couple of sensors, proximity, temperature, and like the controller, the dial thing. And it's got an effector that controls, the HVAC system. And it's trying to, what differentiates it from a traditional thermostat is that it's taking this input from this dial, but also projecting that to a number of other features like, whether it's a weekend or a weekday or whether someone's home and all this other thing, and creating a more rich or complex relationship between the explicit input and the temperature at any given point in time. And it sounds like what you're aspiring to do with Casper is, almost create like a generalized platform for these kinds of relationships between sensors and effectors that might exist in a smart home.
Yeah, precisely. So Nest has a very important vision. Currently, they are limited by that they only have, as you said, a couple of proximity sensors and one dial or something like that. And possibly as they combine with Google Home, a little bit of more supervisory signal. In Casper Homes, we partner with builders. So we have extremely rich data. And just like RoboBrain, it all boils down to what data and what level of representation that you can operate at. So if you operate at, if there is a motion sensor, then I will do this, then this kind of doesn't represent the real world situation, which is quite complex. Like motion sensing can happen for many reasons, not because someone woke up or someone came home, and there are too many variables. So there's a certain level of representation and data that needs to be included to enable some of these interesting features.
Okay. Interesting stuff. Have you, by any chance, come across a company called Ariel?
I may have heard of it, but no, not on the top of my mind.
So I did an interview with them not too long ago, and basically what they do that may be really interesting in this Casper sense is they turn Wi-Fi signals. They can pull some metrics off of your standard Wi-Fi access point, and through data science, machine learning, turn that into very rich representations of what's happening within the space, like the speed at which people are moving, localizing people, the rate at which they're breathing, like really interesting stuff. If you haven't already looked at that, it may be a rich source of new data about what's happening in the space that you can incorporate.
Oh, that's a good pointer. I will look it up.
Yeah, it's Ariel.ai is there. AERIAL, I think. I always misspell it, but you should be able to find it. Ariel Wi-Fi. Cool. Well, this has been a really interesting conversation. I appreciate you taking the time, Ashutosh. Is there anything else that you'd like to add to close the circle on this?
Yeah, I think just last couple of comments on AI and academia and industry. I think for folks who are in industry and building a product, I think this is one thing that I personally found when moving from Stanford Cornell to Casper is there is this interesting substantial impact that AI is making it possible, and it's opening up new challenges in software engineering, product management, and so on. So it has surprisingly become powerful to make products that were not possible before because the scale at which these learning models can operate upon. And we haven't even yet tried to understand the general principles of software engineering and product management with AI. So the questions that you ask, like, is it a general level question, or how a designer is limiting it to wake up? Why are they choosing wake up versus sensors? And then how do you even build a testing framework for AI which operates probabilistically? So these are very interesting challenges that as AI becomes more and more mainstream into products that we have to address.
Absolutely. Absolutely. In fact, just earlier this week, I was at an event. I was speaking at an event down in Dallas that Capital One hosted. And after my talk, I was approached by someone who, raised a very similar point, right? He said, I'm a product person. I don't necessarily need to know all of the details here, around deep learning and some of the other things that I was speaking about. But there is a whole other set of issues that I need to be aware of in terms of how we take advantage of data generally and machine learning in particular to build products that, meet the needs of some set of users. And so there are definitely huge issues there. And I've got on my short list some conversations that I want to bring onto the podcast to, start us thinking about how we approach product from a ML and AI perspective, or ML and AI from a product perspective, more specifically. Sounds like it's something, a point that you're starting to see as well.
Definitely, because Casper is now deployed in real homes with real customers across the globe, and now this AI and real world product comes up.
Awesome. Well, Ashutosh, thank you.
Yeah, thanks a lot for the interview. Interesting conversation.
All right, everyone, that's our show for today. For more information on Ashutosh or any of the topics covered in this episode, head over to twimlai.com/talk/170. If you're a fan of the pod, we'd like to encourage you to pop open your Apple or Google Podcast app and leave us a 5-star rating and review. Your reviews go a long way in helping new listeners find the podcast. As always, thanks so much for listening, and catch you next time.